Thank you, everyone. My name is Scott Tsai. I'm from a more embedded electronics, embedded Linux background. So instead of debugging Python code, this talk would be about debugging C, C++ code with Python. Okay? So this talk is about debugging C or C++ code with help of Python. And we'll go over the easy parts of the GDB Python API. GDB has had that API since about 2010, so it's pretty well deployed by now. And the aim of this talk is to encourage a style of debugging that's more deliberate. Instead of just starting the debugger and banging away at the keyboard like a stupid monkey, you actually write down a plan. You write down your observations, you write down your assumptions. It's like designing an experiment before doing it. All right, so let me ask a few questions from the audience. How many of you have used GDB before? Something like 90%, right? Thank you. So do you know how to set a conditional breakpoint in GDB? That's a breakpoint that doesn't hit every time. It only hits if some expression evaluates to true. So more like 3%. Okay. See, this is the dropout I'm talking about. It's actually useful. It's actually useful. Okay. Do you guys know how to set a conditional breakpoint that only triggers for a specific thread? No. Okay. So implicit in this question is, of course, you've got to be willing to use GDB to debug multi-threaded programs, right? Yeah, most people give up before this point, right? Okay. Okay. So have you used GDB to debug multiple processes? Instead of a single process containing multiple threads, have you debugged multiple processes? Multiple processes. Okay, relatively new feature, about 2 years old. Yeah. So you can actually debug two programs that are doing network communication or remote procedure calls in GDB nowadays. The user interface is still our beloved console-only GDB interface, so I don't fault you guys for not doing it, but it's doable. Okay. So for example, there was a question about basically an JVM inside Apache question. That's a multiple process. Theoretically, you can get it to work with GDB. Practically, it's gonna take some work. Okay. All right, so let's go through the GDB API, the tutorial part of this talk first. How do I get a Python prompt within GDB? So first you start GDB, and then you type Python-interactive. At this point, you have your familiar Python prompt, right? So if you have your laptop out, I encourage you to try along. Right. So the problem is that you'll find that at this point, although you have a Python prompt, you don't have code completion. Okay? So life is just really painful if you're used to coding under IPython or PyCharm and you're used to code completion, and within GDB you have nothing. Okay. So like this, if you only remember one thing from this talk, this is the trick to remember. So we want code completion. IPython can give us code completion within GDB. So the two magic lines that you want to type is, import IPython, and then ipython.embed kernel. So the term kernel here refers to a computational kernel, as in a Python process that's used for computation. That's an IPython terminology, right? Basically, what it's doing is that within the GDB process, we're running the IPython main loop, and then it accepts a TCP connection, so we can open a separate terminal, and then we can connect to that IPython kernel instance, or you can actually open an IPython notebook within your browser and connect to that IPython kernel instance, and then we have tab completion. All right, let's take a look at how this works. So like setting up the environment is like 50% of the challenge when using GDB. So I'm gonna take some time. So I have a file here with only 2 lines. Import IPython, ipython.embed kernel. Just memorize these 2 lines, okay? So at this point, the output here, that's from IPython. The IPython main loop is running and ready to accept input. So this is like connecting your front end to your back end, right? So at this point, I've opened another terminal tab, and I've connected IPython, the IPython console, to the one running GDB. yay, we have tab completion. Right. So this is like half the struggle, right? So it's the difference between something you're willing to play with and something you don't want to touch. It's okay. So now that you have this working, just open the GDB manual. They have a section on the Python API, and everything else I'm going to talk about you can ignore, right? You can learn the rest on yourselves. Okay, well, let me repeat. If there's only one thing you remember, this is the trick, okay? All right. So tab completion works, great, okay. So anything that, so there are two main API entry points for the GDB Python API. One is called parse and evaluate. It's shortened to parse and eval. So any C++ expression that you would type after print in the GDB prompt, you would pass as a string to gdb.parse and evaluate. At this point, you have a GDB value. And from the GDB value, you can use its API to get its type, to get its actual numerical value, and to do all sorts of other things with it. Let's take a look. So the other, besides parse and eval, the other API entry point is execute. Execute takes a string. Any command that you would type into GDB, you can pass as a string to gdb.execute in the Python world. Oh, I don't have, this is something I don't have an up-to-date debug info installed for the user bin true program. Okay, I'll get to that. Let's try something else. So I switched the program that I'm debugging from bin true to Python 3 from the Anaconda 3 installation. It starts, it's a breakpoint is being hit in the main function. So at this point, you have your familiar argc variable from the command line, and you get a GDB value. And you have tab completion. So you see that value fetching is lazy. So copying a value from the program that you're debugging to the debugger actually involves some memory copying and API access overhead. So until you force the GDB API to fetch the value, you just remember which values you want to fetch within a variable. It doesn't actually do it. So to force it to fetch memory, you coerce it to the int or long in Python 2. So this is the part. This is the part where we look inside the CPython implementation. So it's the same trick applied to Python 3. And if we do that, we can look up global type names. For example, the PyDict object, that's a type name within the CPython implementation. You can look up the type, and then you can, using the .pointer method, construct a pointer to that type. So that's how you construct composite types in the Python API. At this point, I want to digress a bit on what you need to set up for this part to work. So if you actually try this on your laptop, chances are it's not going to work, right? The reason it's not going to work, it's not that the IPython would fail, it's that the lookup type would fail at this stage. Is that by default, if you're on Ubuntu, by default, the Python interpreter is not shipped with debug info. So what exactly is debug info? Debug info is the stuff that is the extra stuff that gets generated when you pass -g to GCC, right? So how large is debug info compared to the actual code? Let's look at an example. So for a minimal C program with just an empty main function, if I compile with and without with -g, so it's an empty program, but the file size is still 9.3K. And if you want to analyze which part is the debug info and which part is the actual code, so EU-strip is from elfutils. EU-strip would separate the debug info from the code that's only used for execution. And if we look at the size again, so the debug info is almost as large as the code. And if we passed -g3 to record C and C++ macros within the debug info will grow to about twice as large, okay? So The reason that Ubuntu ships a Python interpreter without debug info is for the download size. It more than doubles your binary size, right? But we need debug info for the rest of the talk. The tricks that I'm going to show in the rest of the talk will be meaningful. If you don't have debug info, you're debugging at an assembler level, which we all love, right? I know, I love it, yeah. If you're building a C extension that's using setup tools or disutils or whatever, to get debug info, you want to export the C flags environment variable. So just pass whatever you would pass to GCC, including -O for optimization and -G for generating debug info before invoking setup.py build. It's not done by default, okay? Okay, let's repeat. Without debug info, you get registers, you get assembler. You don't get function names, you don't get type names, you don't get variable names, right? Okay. So for C extensions, build with -G. Okay. So the next question is that, so for the binaries that I'm currently using, either on my development machine or in my production systems, do they have debug info? Okay, so the answer is kind of involved. Debug info, so this is for ELF files. It's slightly different on the Mac and on Windows, but the principles are the same. So the details that I'm going to discuss now, it applies to doing Python development on Linux. It applies for doing embedded development on bare metal machines using ELF format executable files. And it applies to Android because Android uses ELF, but for Macs, it's slightly different. Okay. So ELF, that's the binary file format. That's the most widely used one. So to programmatically determine whether the binaries I'm using have debug info, you want to look for the .debug-info section. So if your binary have it, in all likelihood it does have debug info. But so as I've shown with EU.strip, you can actually separate the debug info from the binary, right? So this mechanism, the EU strip mechanism, we something called that separate debug info files. Its theory of operation is that there is a .gnu debug link section that's recorded. It records the file name where to look for the debug info within the binary file. Let me rephrase. Basically, debug info is large, right? So we want to ship the debug info separate from the executable. So what we do is that within the executable, we add a separate section called a debug link that records the file name that's to look for the separate debug info. And then we ship the debug info in a separate file. So this is like .pdb files under Visual Studio. GDB could use this .gnu debug link mechanism, or it could use a build ID to look up debug info. A build ID is just basically like a checksum for the binary. For the ELF sections, for the sections within our executable files that are used to store debug info, they always start with .debug_. So let's just gloss over this. Basically, just look for .debug_info to determine whether you have it or not. Okay. So I'm going to write a simple Python script to determine whether you have debug info or not. And I'm going to rely on an external library, PyElf_tools. So you want PyElf tools. This is by Ali Bendersky. I believe he's currently working at Google. Great work, useful. So just install PyElf tools. And we open any binary or shared object file as shared object. That's a DLL, right? So we open the file and we look for a section by name. For example, we could look for .debug_info, and if it returns none, the section doesn't exist. If it returns a section object, you can read the raw bytes. And then you look up the structure definition on the web for how to interpret that binary file. So this is about the separate debug info mechanism. Suppose user bin ls has a debug link of ls.debug and a build ID of abcdef1234. GDB would actually look for the debug info file in this list of directories. Basically, there's a search path, rather like a Python path. If you've got everything right at this point, debugging will work. If you have it, if you don't get it right, it's not going to work, right? Okay. So Linux distributions, they actually do provide debug info as a separate download. So if you're on Red Hat or Fedora, there's a one-line command that you execute. debug info install. And you get the debug info first in the package. If you're on Ubuntu, you need to add three. You need to add 3 repository first. And then you install the package with an extra -dbg or -dbg sym suffix. And so they provide their debug info as separate downloads. And this is the mechanism that GDB used to look it up, right? Okay. So the good news is that the Anaconda scientific Linux distribution, it actually ships with the CPython with debug info. So that's the good news. The bad news is that not everything in that 300 megabyte download has debug info. So the Python interpreter has it, NumPy has it. Some external libraries like zlib, they don't have it. It's just, I don't understand why they do this, but it's not very consistent. Maybe to reduce overall download size, but that's what I do. Just a reminder, the debug info stuff is all for, in order for debugging Python, the Python interpreter to work, in order for looking up a type by name within the Python interpreter to work, you need debug info for the Python interpreter. So the GDB Python API was originally created to implement pretty printers, as in print out a custom data structure in a way that looks good. So I'm going to go over a few signs for a pretty printer. So we implement a regular Python class that has a single method, toString. So the reason they didn't use underlying string is just that, well, they didn't like it. Anyway, the GDB developers decided to do it this way. So the dictionary-like access here, it's actually doing a C structure. It's actually accessing a member within a C structure. So it's accessing the field mdata plus in the std string within the C++ standard library. So the std string printer is the printer class. A pretty printer has 3 pieces. You have the printer class, you have the lookup function. The lookup function accepts a value and either returns a pretty printer instantiated for that value or returns none. None indicates that it doesn't know how to pretty print it. So this string lookup function example, this is from the GDB manual. It does a regular expression match on the tag. The tag is something that GDB synthesizes from the type of the C variable. Okay. And then you register your lookup function to a global list of pretty printers. And this is basically how you do data structure pretty print in Python. So you have the actual class that pretty prints it. You have a lookup function that either returns a pretty printer or returns none for values that it doesn't know how to print. And you register the lookup function to a global list. Okay, let me give my second example. We're going to implement a new GDB convenience function. Okay, so what's a convenient function in GDB? It's something that looks like a function, but it starts with a $ in GDB. So you can use these in GDB expressions to help your debugging. So I'm going to show you how to implement a convenience function called instruction length. It takes an address that points to a machine instruction, and it's going to print the number of bytes that the instruction takes up. And just from the value 3 here, you can see that we're probably on x86, right? If you're on ARM, it would be either 4 for ARM mode or 2 for thumb mode. Right? So, okay. So how do you get the length of an instruction in GDB? So we examine by 2 instructions starting from our program counter. So we dump 2 instructions starting from the program counter. So instruction 1, compare. Instruction 2, push. The difference between the starting addresses of the 2 instructions is the length of the first one, right? So we could see that the compare instruction takes 3 bytes because that's the value that's this 4012 echo 3 value minus 4012 echo 0. So the last value in our interactive session is the echo 3 one. And if we do a subtraction here, we get the value 3. So this is an interactive session. If you translate this into Python code, it looks like this. So a regular Python function here, we take a string, that's an address expression. We pass that to the examine command. And so we are using gdb.execute here. Any command that you would type interactively, you can pass to gdb.execute, right? So we're using toString equals true here to stop GDB from printing to the console. And then we do two type coercions. The last value that we have, we parse and evaluate it and coerce it to an int. The last value would be the address of the second instruction. And the value from our original address instruction, that would be the starting instruction. So their difference is the length of the first instruction. Okay. And then we have some boilerplate. We implement a class that inherits from gdb.function. And it has a single method invoke that takes the number of argument our command takes, our convenience function takes. And it calls our instruction length function that does the actual work. Oh, a bit of Python 2ism. This should be int here. So, and then we instantiate our class, instruction length class. And then within our interactive GDB sessions, we could either pass the name of the source file we just wrote to -x, or we could source the file within GDB. And then we can use the $ instruction length convenience function as if it's built into GDB. And actually, GDB nowadays have quite a few convenience functions that's actually implemented in Python. All right. So in this session, we see that, right, the first instruction, the compare instructions is indeed 3 bytes, right here. Multiprocess debugging. So this is a relatively new GDB feature. So this is a made-up example, right? Okay. So suppose we have a simple C program that uses system to launch an external process. And the program that you really want to debug is the one that's launched. That's the program I want to debug. You're not interested in debugging the launcher. And within program I want to debug is just hello world. So here are the GDB commands to do multi-process debugging. Oh, the font size may be a bit small here. So the key part is this add inferior command. And inferior in GDB terminology refers to a program under debug. Well, more precisely, it refers to a process under debug. So to add an inferior is to say that we want to debug 2 processes. So we add an inferior that's running the executable program I want to debug. We set a breakpoint. We're using the breakpoint syntax where we specify it's line 5 from this .c file. And then we start the program. And after a run would only return after a breakpoint hit. So the only breakpoint we have is the one on line 5, that's the printf. So after run, it means our breakpoint was hit in the second process. We switch to inferior 3, and then we do a backtrace. Inferior 3, we're switching between processes. That's being debugged under GDB. So it's like this. So we just run the script as a non-interactive session. Oops. Okay, and then we have a breakpoint hit in the second process, and the breakpoint is indeed on the printf line. We do a backtrace. It's just it's just from printf to main, right? So this is just to show you that GDB can do multiple process debugging. Okay, so pretty much the last topic I want to discuss is debugging optimized code. Debugging optimized codes under GDB, not pleasant, doesn't really work well, right? So trouble number 1 is that you'll see a lot of value optimized out when you're debugging optimized code under GDB. And the trouble number 2 is that the optimizing compiler does amazing control flow transformations to your C code. So you can have mutually recursive functions that gets unwrapped into a loop. So if you're trying to single step it, it could look nothing like your source code, right? So what's the solution? I don't have any solution for now. Basically, you do it in assembly, right? Yeah. And so the only theoretically better solution is to synthesize C code from the optimized assembly code, but it's not implemented in any production debugger that I know. So to debug optimized code in GDB today, you pretty much need to do it at the assembler level. Okay, so that's a simple example. we have a C function called login that takes a null terminated string password. It copies it to its internal buffer, does a string compare. If the password is equal to a master password, we set isLogin to true. And isLogin starts off false, and we return the isLogin value. So if we compile this function with optimization on, what would happen is that the local variable isLogin, it would never take up memory, right? Because we never take its address and we never force it to be in memory, it would just be in a register. Okay. So this is the main function part of the program. It's just you need the right number of command line arguments and it does the compare. So this is from I guess a reverse engineering tutorial where your goal is to use GDB to alter the control flow of this program so that no matter what password you type, it always compares, you always get authenticated. So how do you do this? Okay. So when you compile with optimization on, unless you take the address of a local variable like this, so mostly local variables won't be stored on the stack. They would just be in registers, or if you don't use it, they're not even in registers. So let's take a look at how GCC handles it. So we compile this with optimization on, and then we use the GDB command info scope login. Login is the name of the function, and bear with me here. This is the output of info scope login. So this is like looking at the implementation of the debugger. What this is trying to say is that for the local variable is logged in, so when your instruction pointer is between the ranges 40064C and 40066 echo, the variable has the constant value 0. If your instruction pointer is between 40066 echo and 400673, you need to evaluate this expression here in a stack machine that's specified in the Debug Info standard. We'll look at what it means here. So this is a disassembly dump of the C code. So it moves the structure, it moves master password into the register RSI, and then it moves the string that it's going to compare with to RDI, and then it calls string compare. And the return value of string compare is in EAX. So it tests if EAX is 0, and if it's 0, it sets the equality flag to AL, overriding the return value of string compare. So this is the x86-64 exemplar. Right? This is using the Linux calling convention. So the first argument to a function is RDI. The second argument to a function is RSI. Right? So if we compare this slide with the previous slide, we'll see that when you're running the machine code in the range of 66 echo to 673, that's here, right? So the value of is logged in would be, you have to evaluate this dwarf expression in your stack machine. And what this expression is basically saying is that fetch register RAX left shifted by 32 bits, so that the upper 32, RAX is 64 bits, right? When you left shifted by 32, you get rid of the upper half. And then we compare it to the constant literal 0, and that's the value of is logged in. So it's basically saying the value of is logged in depends on the return value of string compare, which would be an RAX. So if we want to change the behavior of this function, it's actually better to set a breakpoint at the point where string compare returns and modify the RAX register. And there is no memory location that would correspond to the is logged in local variable. Right. So it's better to just set a breakpoint on the set equality flag instruction, single step it, and just always change AL to 1. And this is easier than changing is logged in. Okay, so that's my last example. Questions?
Thanks for the amazing summary. It's very useful to me, and really thanks. I appreciate those detailed summary. And I am wondering which case or which project, or say which scenario you apply those skills recently in your job or.
So it's actually useful for some different scenarios. It's actually useful for when you're just tracing, when you want to understand how the program works. You can get a call graph on how the function calls, the relation between function calls in the program. And the problem with printing every function call is that you forget the forest for the trees, right? So at this point, you want to set breakpoints only on the critical parts. For example, maybe only on the methods of a certain class. So what we could do is that you would use use the debug info to look up how many methods a class has, and then programmatically set breakpoints on them using Python. So that's one use case I can think of. Another recent use case is actually I was following an online course on operating systems, and they got to the point of they were writing the context switch code. So the CPU was going into privilege mode, going back to user mode, and you were switching contexts, running different threads. And by using Python to programmatically just clarify which context and which mode the CPU is in, I managed, it's a lot easier, the program becomes a lot easier to understand. So those are, I guess, for tracing, right? An example for debugging is, so let's say you have a bug somewhere within a C++ class. I can write an extra method that does a consistency check on the member data of the C++ class. And then I have the problem of where do I call this consistency check function, right? So I could set breakpoints on every method within the class, and then use the GDB Python API to call my consistent check function. So you could do something similar to malloc debugging.
Do you think it's practical to use this kind of tools to help debugging a hybrid system that has both Python and C or C++?
So there is a Red Hat developer called David Malcolm. So if you look at like PyCon US, I believe 2010, he gave several talks related to that topic. The general problem was so I played a lot with his code while I was learning this stuff. So you run into the value optimized out problems quite a bit when you're trying to basically use the lower level hooks in CPython. So it's doable, but you'll need some architecture specific code that only works on, say, the x86 64 version of CPython. But when you're debugging a really complex problem, I still think this approach is preferable because although it may take some time, it's systematic, and the knowledge that you previously had from C++ development, from computer architecture and all that, you can apply it when you're using this system. So
does that mean?
Yeah, basically the harder the problem,
yeah.
The harder the problem, the more practical this approach is. If the problem is trivial, it's not worth it. That's what I'm trying to say.
You mentioned systematic approach. Does that mean that what we did with this Python extension to GDB can be turned into a library or something like that?
So, because GDB itself is not structured as a C library, so if we try to use this as a library, it's not very convenient. What you would have to do is that you need to start a separate process to run GDB, and then you talk RPC with the GDB process. Doable, I've done it. Yeah.
Sorry, it's new to me basically for using the GDBs. But in my past experiences using the Windbg to do the debugging with like a writing extension, and it's very similar.
Sorry, could you repeat what you were using Windbg?
Yeah, so I would like to know is this way, is there any kind of, I mean, in past is like you need to write using C++ to write the debugging extension in the Windbg. And so I would like to know is there any equivalent for the Windbg for using the Python to write in the Windbg extension?
So I would have to look it up, but I believe there is. That's for Windbg, right? For IDA Pro from Hexrays. Have you used IDA Pro? For IDA Pro, there definitely is. Right? So I'm going to generic your question a bit for other debuggers. So LLDB on the Mac has a Python API. That's basically equivalent in power. So I would have to look up whether Windbg has one. But Microsoft provides a DLL that basically abstracts some of their debugger functions.
Yeah.
Yeah, so we could use C types and use I forgot the name of the DLL.
But is there any Python like you showed in previous for the Python interactive to do extra layer so that I can use in the Python
I see. So you have a better development environment when you're doing Windbg, right?
Yeah.
I'm going to guess that my trick probably works in Windbg as well. I've never tried it. Well, come find me and let's try it.
Okay, thanks.
Yeah. Okay, we thank Scott Tsai. This is for question.